In this video, we're going to practice on a classic problem that involves circular motion in the horizontal plane while balancing the forces in vertical direction. Previously, we've practiced problems in pure horizontal circular motion, like a ball orbiting on a table, or pure vertical circular motion, like a roller coaster loop. Here, let's see how we can handle a scenario where we have both directions involved. So here we have a rock tied to a string and is orbiting in a horizontal circle. And the circle has a radius r of 1.5 meter and the speed v of the rock is constant 10 meter per second. Our goal is to determine the angle theta the string makes with the horizontal. As with any dynamics problem, the first step is to draw a free body diagram. So what forces act on the rock? First, we have the gravity, Fg, which is the weight of the rock acting straight down. And second, we have the tension force, Fp, which acts along the string. Now, because the tension force Ft is not purely horizontal or vertical, we need to decompose it into its horizontal and vertical components. To decompose Ft, we create a right-angled triangle. One side is along the horizontal axis, and the other side is along the vertical axis. And this horizontal one is Ft in x direction, and the vertical one is Ft in y direction. And Ftx is the adjacent side of the angle theta. So for this horizontal component, Ftx divided by the Ft, which is the hypotenuse of this right-angled triangle, it is equals to cosine theta. So we have Ftx equals to Ft cosine theta. So for this vertical component, Fty is the opposite side of the angle theta. So we have Fty component divided by Ft is equal to, so opposite side divided by hypotenuse is sine theta. So we have Fty component is Ft sine theta. Now we are ready to find the net force in each direction. Starting with the vertical direction, there are two forces. One is the Fg, the other is the y component of Ft. So we have F net is Fg minus Fty. And Fg is the weight of the rock. It is the product of the mass and the gravitational acceleration. And Fty is Ft sine theta, right? In the vertical direction, the rock stays at the same height. The rock is orbiting in this horizontal plane, so there's no motion up or down, meaning it's not accelerating vertically, right? So the forces in this vertical direction are balanced, and the net force in this vertical direction is 0. So we have mg equals to Ft sine theta. Since we have both Ft and theta as unknowns in this equation, we can't solve for theta yet. So now let's see what we can get from the horizontal direction. The only force in this horizontal direction is Ftx. So the F net in this horizontal direction goes to Ftx. In this direction, the rock is moving in a circular orbit. While the speed is constant, its direction is changing, which means there's acceleration horizontally. And this acceleration is centripetal acceleration, right? The centripetal acceleration only changes the direction of the velocity while maintaining a constant speed. So as soon as there's a centripetal acceleration, this horizontal net force will not be 0, and it will be equals to the centripetal force, Fc, which is always directed towards the center of the circle. So we have Fc equals Ftx. The formula of the centripetal force is m multiplied by v squared over r. It equals to Ftx is Ft cosine theta. Now we have two equations. So this is our equation 1, and this is equation 2. To solve for the angle theta, let's use the substitution method. by first isolating the tension Ft in equation 1. From the first equation, we can get Ft equals to mg divided by sine theta. Now we substitute this expression for the Ft in equation 2. So we have mv squared over r equals to mg over sine theta, then multiplied by cosine theta. Now right away we can cancel the mass from both sides. So now you can see the angle is actually independent of the rock's mass, right? And then we are left with v squared over r equals to g multiplied by cosine theta over sine theta. Now cosine theta divided by sine theta is 1 over tangent theta, right? So sine theta over cosine theta is tangent theta. So here we have cosine theta over sine theta, so it's 1 over tangent theta. Now let's rearrange this equation and put angles on the left side and all other variables on the left side. Okay, so we have tangent theta equals to g r over v squared. Now let's plug in the values. We have tangent theta equals to g is 9.8 meter per square second, and the radius r is 1.5 meter, divided by the speed is 10 meter per second, then squared. So it equals to 0.147. And finally, to get theta, we take the inverse tangent of 0.147. So we get theta is 8.35 degrees. And there you have it. The angle of the string makes with the horizontal is approximately 8.35 degrees.